Welcome back. This is the second and final video, hopefully for now, that did not process when I first made it. So here we are again. I can use proportional thinking to solve problems with scale drawings and models is our learning target, and it's already pre-written, and so follow along from there. All right, our expectations are to think, pause, take your time, make sure your handwriting is legible so you can read it for your future self, because that's the goal, is for you to reference this. It's not just to hear it and to learn it or process it. My goal is that you learn it through the practice that we do together. This just introduces some examples and how you would apply and build on what we've already been learning. So here's our after the video and onto our notes. So we are on solve problems with scale models. It's on page 9. So solve problems with scale models, page 9. So this should be in your table of contents. Moving on to page 9. Okay, so we are going to start off with the title, the page number, learning target, 2 definitions, and then we're doing 4 examples. I labeled the examples A, B, C, and D. I'm going horizontally because they are word problems, so just an FYI. So we're going to draw a lot today, and that way we have more room for drawing. I'm doing the 4 examples horizontally. Repeat after me. 4 examples horizontally. Okay, if not, just do this with your fingers. That way you understand what horizontally means. So pause here. Make sure you have these definitions down. A scale drawing is a proportional 2D, so it's a flat drawing of an object. A scale model is a proportional 3D model of an object. So 2D is something flat. An architect would use blueprints to represent this scale so people know how big the bathrooms are, or how big a classroom size will be, how wide the hallways are, so you actually have room to walk in them, or in like a kitchen, how much distance do you have between the island and the counter space? Like if you have a dishwasher, and making sure that actually has space to open, and it's not just going to get stuck and just never open, or if it clashes with the refrigerator door. A scale model would be a 3D actual shape of it, so you could make that with paper, you can make that with foam, but something actually standing so that you could then visualize what the house or what the cityscape would look like. If you have an apartment building here, but you have a grocery store right next door, what would their sight lines look like? Because you actually see the height as well, and not just how much, like they're 10 feet apart, space on my blueprint. So my random drawing of a triangle here was to say that this 5 centimeters is to scale. If this was actually, like, I have a scale. This is not 5 centimeters itself. It's representing 5 centimeters, but then sometimes things aren't to scale, because if this is 5 centimeters, but then I say, well, this is 10 centimeters and this is 2 centimeters, then this whole triangle itself is not to scale, because those 3 lengths are the same. They are not proportional to a scale factor, where 5 centimeters is this and 10 centimeters is twice that. So thinking about that, most drawings in math that I'm using in notes, I'm not being precise. They are not to scale. They are not scale drawings. But if you're going to be precise and you're making an object, or you're wanting to see what the object would be, so I have it, oh, they're over there. Actually, I'll bring them out. Why not? While you copy that. Okay, so this is just more proof that your math teacher is really funky. But I did this. I always rearranged my room. So my bedroom was always rearranged, and I always made a scale model. It took me until we moved to realize my scale model was not to scale, because I thought my room was a 12-foot by 12-foot room. It was 11 by 13, and no wonder my scale models never actually fit. But in this new house, I made one. What was this? Okay, this is the kitchen. So I made one of our kitchen. So I made an outlet that looks like this. And I put dimensions down here loosely, and then my scale, I didn't actually write a scale actually. I think my typical scale is that 1 inch is a foot. It's usually what I use. And then knowing that, I then make mini things. So I have a mini stove that I can rearrange, and I have an arrow as to where it actually opens. I have a mini fridge that opens. I have my counter depth. So this is how deep the counter is when I can move it around to measure out. I have a cabinet depth because those are actually more, they're not as deep as your counters cabinets, another counter and another cabinet because we have several walls of counters and cabinets. And then we made a summer project of making a patio in our backyard. And, oh, I want to redo my closet. So I made a closet map of like, what would my dream closet be like? What does it look like now? How long do I have to? So apparently my closet rod is up. Oh, how far up is it? I want to say like 5.5 feet. I don't remember how far up it is now. Yeah, I think it's up 60 inches right now, but 40 and 40 is typical height. And so mine's really low compared to past closets that I've had. And then I made a map of our house and our lawn of where is concrete, where is flower bed, where is grass. So this is not to scale, but I labeled each of the dimensions. So then I could break up my lawn into different rectangles and find the areas of each of the rectangles. And now I know how much concrete we have, how much grass we have, which helped my husband because he wanted to know how much seed we would need if we were to plant new seed, and then how much like fertilizer he needs because it's always sold. This serves 1,000 square feet. Well, if you know how many square feet you have, then you know how much you can buy or need to buy or can overbuy or underbuy. So anyway, scale models and scale drawings are my life. I have used those so many times in my life. Knowing that, here's our first example. Okay, I'm going to use this to hide that. Okay, so the Minnesota Wild is our professional hockey team, and they play at Xcel Energy Center in St. Paul. Twins are Minnesota's professional baseball team, and they play at Target Field in Minneapolis. On a map, they're only 3 inches apart, the Xcel Energy Center and the Target Field. But it takes longer to get there because they're not really only 3 inches apart. Instead, on the map, their scale is 1 inch is to 4 miles versus mine is typically 1 inch is a foot. But 1 inch to 4 miles. So I want to know how far apart are they in real life? Now, they gave me a ratio, 1 inch to 4 miles. That means that I know one of my fractions is going to be 1 inch to 4 miles. I don't know the other ratio completely, so I need to figure out what's compared to what. Inches and miles, they're both two different units. So inches gets its own row because they're the exact same together. They're being compared together. And miles gets its own row. Notice that I don't have inches and miles being compared to each other with it. I know 1 inch goes with 4 miles because it told me. I'm not comparing 3 inches to 4 miles. They did not tell me they have anything in common. Okay? So I know 1 inch to 4 miles, and I have 3 inches to I don't know how many miles. So now I need to figure out scale factor. 1 times 4 gets me 4 miles. So 3 inches times 4 will get me 12 miles as my final answer. Okay. Example B. Okay. There we go. Okay, so the Mexican flag is 63 inches long and 36 inches wide, and I want to know, is the drawing that is over here similar to that flag? So this was a piece of paper, 11 inches by 8.5 inches. So on a piece of paper, printer paper, normal paper, we drew the green, we drew the white, we drew the red, and we drew in the middle the eagle with the olive branch and the snake, which is represented by my circle because I'm not going to draw it that detailed. You can go Google it. So on this Mexican flag piece of paper, is that similar dimensions to the Mexican flag in real life? So let's see, 63 inches long and 36 inches wide. I know those are both dimensions with a Mexican flag, so they get compared together. And I know that 63 is the longest section, so 11 inches gets compared to that because of length, and this is width. Now, I don't know if these are similar. It's asking if they're similar, so I'm gonna put a question mark above the equal sign until I know that they are similar. Again, I'm using my calculator. I figure out the scale factor from one to the other. Those are my two scale factors, so check on your calculator. Can you get those two numbers? This is 5.7272727272727. It keeps going. There's a bar on top for that. And then Are the scale factors the same? If they are similar. If they're not, it is not similar. Okay, they are not similar. And example C, there we go. Oh, actually, I'll do that. So there's a student desk, student desk that is 30 inches by 18 inches, and it is similar to this little tilde or squiggle means similar to this teacher desk that is 50 inches by some unknown width. I don't know how wide the teacher desk is, but I want to know how wide the teacher desk is so I know how far I can move it in a scale model of the room, etc. So pause the video. I want you to make the proportion. Remember, corresponding, similar figure, same figure. Okay, you should get something like this. If you had this one exactly, then you would have 1 2/3 be your scale factor. Knowing that, use your calculator, figure out your answer. Should be 30 inches. All right, again, I'm using W because that was the unknown variable that I used. So then for D, okay, I'm going to show this whole one. All right, because I want to go over it. So copy it all down, pause here, and then hit play. This is a really common question because you're going to see this in the next 5 years several times, especially in geometry, okay, especially in high school. So shadows are created by light. This is a lamppost. I used yellow because it has a light, and you might be able to see there's a yellow line coming down here. So the light hits the top of the person's head, and that represents this shadow here. That's why the shadow stops, because there is nothing else up here for the light to hit and create a shadow. These are really helpful. This is how people learned how tall the pyramids are, because the pyramids in Egypt are so well structured. You can't get into them. You can't just stick a stick down the middle and say, I hit ground. This is how tall it is. You can't do that. But with the light hitting at certain angles, the pyramids make a bunch of triangles, and we can see where that top point then hits on the ground as a shadow, and we can tell using proportions then how tall the triangle is. So this is a lamppost. I don't know how tall it is. Granted, it's labeled now because I did the math. But assuming I don't know how tall the lamppost is, but I do know this person is 6 feet tall. So if this person is 6 feet, and I know, because I can measure, there's a second person running around measuring all of these things, that I know how long there's a shorter person measuring this. We'll do that. So one person is 6 foot. The shorter person is running around and measuring, hey, I know you're 6 foot, I know your shadow is 10 feet currently, and I know you're 20 feet away from the lamppost. Notice that this little tick mark, that apostrophe, means feet, all right? If you have 2 tick marks or quotations, that means inches. So 6 foot person is 10 feet away, so 6 is being related to 10, and then the height, I just used H, so the height of the person, height of the lamppost. They mean the same thing. They're similar to each other, so they're being compared, 6 and H. 6 and 10 are in the same triangle, this green triangle here, so they're being related. And then the tan triangle is tricky because it has a side here that corresponds with 6. There's this side, which is called the hypotenuse, if you care, which corresponds to this green side. And then this whole bottom side corresponds to the shadow. So the shadow is 10 feet. The whole bottom side is 30 because it's 20 plus 10. Notice this drawing is not to scale because this 20 feet is actually looking smaller than the 10 feet. Labels are what counts, all right? Scale drawings are awesome, but they take a lot of time to do. So, knowing that, I have 10 related to 30, I have 6 related to H, I have 6 related to 10, and I have H related to 30. Figure out, make sure in your brain you know why this is set up and how it is set up. If you're stuck, come ask me for questions. Go ask your teacher for questions. Ask the person next to you, why does this make sense? Once you have it and set up, you've solved this for several lessons for several weeks by now, okay? So 10 times 3 gives you 30. So 6 times what gets you H? H is going to be 18 feet. To actually answer the question, how many times taller is the streetlight than the person? The answer would be 3 times because this lamppost is 3 people tall. Again, not to scale. So now you know what not to scale means, even though this would be to scale. My little fridge, and my little stove, and I can stick it in my kitchen. Because right now, I even like traced around them. My fridge is like right there in my kitchen. Or no, it's not. My fridge is actually here in my kitchen. This is my stove. And then I didn't cut out the counters exactly. I just cut out their depth. So that's my counter depth. And then I have my cabinet depth above it. So you can tell, like, there's a lot of counter space in front of your cabinets. Like, who knew they weren't actually that deep? But the base cabinets are that deep because they're under the counter. So it's just wild. So, and you can't have like a fridge door opening so far because I have a wall right here. So that wall does block part of my fridge. So having scale factors and knowing like this is how much farther it comes out, this is really shallow, knowing how far in it eats, because there's a closet out in the hall over here, but to know exactly where they line up would be really key. And knowing that, like, okay, this actually I think, I don't know if it keeps going or not. I guess it doesn't, because I have counter all the way here, and then I have a door, but then I have more room. So, anyway, there's lots of numbers and planning that we can go into. And that was the end of our video. I went over, but hey, you got to learn more about my life and how I do scale drawings, because I've done them since probably 2nd or 3rd grade, I think, is when I first started measuring my room to rearrange things. Now there's less furniture that I can rearrange. We rearranged the living room, and I've rearranged this half of my office/bedroom because of the dresser a little more. But some furniture pieces are just too heavy, and now they're shared spaces, so I can't just rearrange them when I want, sadly. So, have a great day. Thanks for listening to all my scale troubles.